All right, hello everybody, and welcome to presentation 3. Today we're going to talk about number systems. I'll begin with an overview of what I'm going to discuss today. So we're going to talk about how we write numbers and why. Now this, on the surface, seems like a really simple topic. And none of the ideas I'm going to present today are super complex. However, they are significant. And so, though this will be a bit of a review, it will be this presentation will be covering topics that are going to be very useful for us, simple ideas that will be very useful for us as we move forward, talking about base n numbers and binary numbers, eventually talking about base conversion, and then how we do math on numbers represented in binary, for instance. So again, some of these ideas may seem dull and mundane at first. I ask you to please pay attention because in my experience, for many of us, even though we've seen this information before, we saw it so long ago and in a context that was maybe not as accessible to us as it is now. And so it's very common for students to actually, in my experience, to actually say, oh, well, I understand that better now. So even if this seems elementary, please play along and try to pay attention. All right, so let's jump right in. We're going to start with a bit of a story, okay? So it's a completely fake story, but it presents some very true ideas. So, long, long ago in a land that never existed, we'll begin with an individual named Matthew. His name is not spelled incorrectly. He goes by Math for short. Okay, that's my funny, not so funny joke for the day. All right, Matthew is a shepherd. All right, he's a keeper of sheep. Yes, they're noisy sheep. Okay, so Matthew's unhappy. Well, why is he unhappy? Well, he's unhappy because in his civilization there are no symbolic numbers. What does this mean? Well, it means that as a shepherd he's forced to bring his sheep with him everywhere in order to barter. So if he wants bread or a new fancy staff or a robe or any of the things he doesn't make himself, he has to trade sheep for these things. And because they don't have number systems, ways of tracking how many of things there are, he has to bring these sheep everywhere. And sheep are big, noisy, smelly, and not smart. So if any of you have worked with sheep, you may use stronger words, but they're not the most intelligent animal, which says something about the fact that the Lord compares us to sheep. Matthew has an idea. It occurs to him that he could use symbols to represent his sheep, and then maybe he could pack around these symbols instead of packing around his sheep. You see the extent of my artistic abilities right there on the left. The basic idea he has is, let's represent one of my animals with a line, just a mark. It could be on a pole, on a rock, on a piece of wax, anything. Okay, but the idea is let's use symbols instead. So this idea ends up working very well. In fact, it works so well that Matthew starts to become wealthy because people want to do business with him because he has this great new way of doing business, and he doesn't have to bring these sheep everywhere that, drop things in the yard and stuff like that. Okay, so it works great, but over time, as Matthew's flock begins to grow because of his high productivity, he starts to run into a bit of an issue. Okay, so as the flock grows, the size of his symbolic representation continues to grow. So Matthew's still not very happy. So he comes up with another idea. He says, well, what if I use more symbols? Okay, and he was just using a base 1 number system there with these things we call hash marks often. So he has this idea, well, I'll use more symbols. So he starts with these symbols that look kind of familiar to us. So he has 10 of them. Now he has one in particular that's significant, that 1 0, that he can use to explicitly indicate there are none of something. So before he just didn't make any marks. Now he actually has a symbol that represents the idea that nothing is there, that there's an absence of something. And we'll see that that's extremely important in a few minutes here. Okay, so we already saw, though, that Matthew has more than 9 sheep, so he needed more symbols. So he reached for the alphabet, and so he gets another 26. Now, temporarily, this works as well, but as his flock continues to grow, he needs still more symbols. And so here I've reached for some from our keyboard that it just turns out Matthew happened to think of on his own. But now he's out of ideas. So we see there's a problem with this idea. Having a different symbol for every value becomes intractable as the number of possible values goes up. Okay, so finally, Matthew has a brilliant idea, and looks like part of it snuck out ahead of time on the bottom there. Pay no attention to the 10 to the 0 on the bottom of the screen. Okay, so Matthew has this brilliant idea. He decides to kind of combine the two he had before and then add something to it. So he's going to start with a set of symbols to work with. So he decides on the first 10, 0 through 9. Then he realizes that he can utilize the position or place of a symbol as part of its meaning. So, for instance, now you can pay attention to the 10 to the 0. This value down here, or this position, if there's a single symbol that's been written, then Matthew will interpret that to mean that number of 10 to the 0s of something. Okay, and 10 to the 0 is, of course, 1. And so this position in the number system will be used to keep track of units, and this is consistent, we'll see, between all base systems. Matthew hasn't realized that yet, but in his scheme he says, okay, so I'm going to work with this idea of 10 symbols, 10 things. So I don't have 10 yet, I've got 10 to the 0, so I have units at this point, so I can have 0 through 9 of those units. Then I will decide that if there's a number written to the left of another number, okay, so we'll call it the second position, then that means I do have tens, and I'm counting them. So here I have 10 to the 1, and so forth for 10 to the second and 10 to the third. So we recognize these again as being the units position, the tens position, the hundreds position, and the thousandths. Okay, and of course this can go on infinitely. So Matthew has just invented a scheme that is very scalable, and we will see just how scalable it is in a moment. So, again, another way of writing Matthew's idea is that in each of these positions, we take the symbol and we will multiply it based on its position by a power of 10. 10 being the base of Matthew's number system. The base representing the number of symbols or digits in that system. Okay, so for instance, well, and I should add, then we'll add all of those symbols in their positions together to have the complete number. And Matthew recognizes that he can represent any number of sheep that he could conceive of in this way. So, for instance, if he has 1,276 sheep, then he could use his number system to write this thusly. Now, it's kind of messy looking, but again, it's the position of the symbol that Matthew zeroed in on to represent the base, or the power of 10, rather, that the digit or symbol is being multiplied by. So we can get rid of the times 10 plus stuff. It's implied by the scheme itself. So 1,276 sheep can be represented then with these 4 symbols or digits. Okay, so now with just 4 symbols, Matthew can represent a lot of sheep. All right, so this is great. Matthew's happy. Okay, so let's recap and make a comparison. So here I have a couple of charts. On the left, then, I'm representing the number of digits on the y-axis relative to the value, or the size or magnitude of the value that we're trying to represent. And in the table on the right, we're talking about then the number of symbols that would be needed in a number system relative to the number of possible values that that number system can represent. Okay, so looking at base 1, we see that there's this 1-to-1 ratio. Okay, so linearly increasing number of digits that are necessary to represent a value if we're just using hash marks. Okay, and that should make sense. If I have 5 things, I need 5 hash marks. If I have 1,000 things, I need 1,000 hash marks. Okay, so though the hash marks are smaller than the things I'm representing, okay, there's still this linear growth in terms of how much space I'm going to need to represent a value, and how cumbersome, by the way, it becomes. All right, on the right, though, we see that with this base 1 number system, there's only one symbol to be used, okay, no matter how many values I conceive of. Okay, now base infinity. All right, so that's what I'm using to represent the second idea that Matthew had, where he said, okay, so I'll create a different symbol for every possible value. Well, that's cool, because that means that I have one digit, one symbol for any possible value that I could write down. Unfortunately, that grows linear. linearly, right? So as the number of values I want to represent grows, the number of symbols that I need in my number system grows at the exact same rate. Okay, so these two are kind of reciprocals of each other, and that's kind of neat to see. All right, and then finally, there's this idea of base n. And Matthew used base 10, but if you think about it, you could use any number, any as your base. So we're just going to talk about this generically and say base n. All right, so how's this work? Well, it turns out then that the number of digits I need to represent a number using a base n place value number system grows at a rate of log n of the value. So the number of digits I need goes up, right? But it goes up very slowly. And in fact, the rate at which it goes up decreases over time, or rather as the values get larger. It only takes one more digit to double the number, in base 10, it takes one more digit to have 10 times the number of possible values. Okay, so every time I add I add a digit, I increase the size of the values that I can represent by n times, right? So this is great. This is very powerful. And when we look at the number of symbols that we need in the number system in general, we see that it stays constant at n. And so we kind of have the best of both worlds here. It's a powerful number system that scales to values of any size, and it does so with a fixed number of symbols. All right. So again, a review of this then. So a base n number in general is speaking of a situation in which n is the number of symbols that we have to work with. Okay, so base 10, we typically use the digits 0 through 9. Base 8, for instance, we would have 0 through 7. Here's base 16. We, like Matthew, run out of digits, so we rely on these other symbols. We just pull them from the alphabet. So the letters A through F represent the values 10 through 15 for base 16. A very common number system for computer scientists to deal with actually is base 16, but also base 2. And we'll see why base 16 is so significant to computer scientists a little later, and why it comes up so much. But base 2 is the one people usually think of, binary. It's base 2 because we have two digits, 0 and 1. The neat thing about this is that if you think of Matthew's scheme, his idea here of using what we refer to as place value, one question we might ask is, well, what's the smallest number of symbols that we could use to make such a system work? Certainly we could use as many as we want, right? You got base 57, base 1000, whatever. You'd simply need to have symbols to represent those values, and then you could use this place value system. But what's the smallest number of symbols we could use? Well, it turns out that it is 2. Binary is the smallest place value system that you can use. And the reason is because in order for place value to work, you need to know the position that something is sitting in. And you need to be able to represent the idea that something does not occupy a position, right? So if I don't have any tens, but I do have hundreds, I need a way to separate and indicate the difference between, for instance, the ones, the tens, and the hundreds. So if I had 101, for example, then I need a 1 in the units place, a 0 in the tens place, and a 1 in the hundreds position. And that 0 is important. If I got rid of it, then I'd have 11, and that's a completely different number according to the scheme. So these two values, okay, the presence of something or the absence of something, are necessary. And as a Latter-day Saint, this is very significant to me in general. It's interesting to see that something and its opposite can be used to create any set of numbers, right? The presence of something or the non-presence of something. And we see this in lots of places in nature, right? Electrons and protons, and so on. So I find this kind of cool. Moving on, though, so yes, base 2 is binary. Let's look at a couple of quick examples as I end this presentation. So the numbers that I have written on the left here are all in base 10. So that's where we're going to start. We're familiar with those numbers. And I just want to give some examples of writing those numbers in other bases. So let's begin with base 8. A good way to think of this initially, when we're new to it, is to ask ourselves, well, what's the largest value in this base, or what's the largest position that I need to occupy? Right? If I start in the units position when I want to represent 10 of something, I'm probably going to run into trouble base 8 I am, because the largest value I can represent in the units position is 7. It's not enough. Okay, so instead of, rather than starting the lowest position, we often will, when we're doing it in this way, where we're just kind of, as we go, trying to figure out the value, we'll start trying to find the largest position we can occupy. So, the 8 to the 0th position is the units position. That's not going to be large enough. 8 to the 1, or to the first power, will give me a value of 8. Okay, now certainly that fits. I can get one of those inside of a 10. All right, so that's a viable option, but I need to make sure, see if I can go further. So 8 to the second power is 64. That's way too large. So I'm going to start at 8 to the first power. And it turns out I can only use one of those. Two of them would be 16, and that's too large. So I've got 1 times 8 to the first power. That leaves me with 2 left over from the 10 I'm trying to represent. So I'm going to add 2 units, or 2 times 10 to the 8th. Okay? All right. Again, using our place value system, then we would simply write this as 1, 2. So we might read that as 12. That would be inaccurate because this is not in base 10. This is in base 8. I don't know of a convenient way to say that other than to simply say 1, 2. Okay, so the number 1, 2 in base 8 is equivalent to the value of 10 in base 10. Okay? To represent the value 10 in base 16, well, that's pretty easy because we can represent up to 15 units in the units position in base 16. So we can grab the 10. So we have 10 times 16 to the 0. Now I've written 10, that's a base 10 value. So ask yourself real quickly, what would the actual value or symbol that I would use in base 16 be? If you answered A, you're correct. Okay, so we would represent the decimal value, the base 10 value 10, as an A in a hexadecimal or base 16 system. Okay, let's look at base 2. So again, using this idea of, well, what's the largest base that I can utilize? 2 to the 3rd is 8. Okay, 2 to the 4th is 16, so that's too high. So 2 to the 3rd is 8, and I can only ever have 1 or none of something in base 2. So I've got an 8, so I've consumed 8 of my 10. I'm not going to use any 2 to the 2nds because 2 to the 2nd is 4, right? And I don't need to add 4 to 8 to get 10. That would be too much, so I put a 0 here, and that's where again we see the significance of 0. I need to indicate I don't need any of these. And then finally, or not finally, but then moving on, we need a 2. So 2 to the first power is shown here. So I want one of those. And then finally, I don't need any units. So 0 times 2 to the 0th. Writing that number down compactly, we have 1, 0, 1, 0. All right. So that's a way, kind of thinking from the top down, that we can convert from one base to another. Moving on to the example of 5, well, I can write the the value of 5 with the digit 5 in base 10 in the units position. Excuse me, the value 5 in the units position of base 8. Turns out I can still use the same symbol in base 16. It gets a little more complicated in base 2. So in this case, I'm going to need a 4, which is going to be in the 2 to the 2nd position. Don't need any 2's, so 2 to the 1 is 0, and I do need a 1. So 2 to the 0th power, I've got a 1 of those. Okay, with representing the value 16 in base 8. So in this case, I can't get high enough in the units position, so I move to 8 to the 1st, where if I have 2 8's, that gives me 16. So I'm good. Now I just need 0 units, and I've written the number. So 2, 0 in base 8 is equivalent to 16 in decimal. In base 16, I'm trying to represent the value 16, and so it should stand out immediately. Well, 1 times 16 to the first power is 16, so I have a 1 and then a 0, the 0 indicating I have no 16 to the 0th powers. Zeroths. How do you say that? Okay, so I have 0 units. We'll just leave it at that. All right, and then finally in base 2, so I have 1 of 2 to the 4th, which is 16. 0 to the 3rd, 0 to the 2nd, 0 to the 1st, and 0 to the 0's. Okay, now for our final act we will look at 1, and we'll see that no matter which base I'm working in, I can represent 1 with the symbol 1. Okay, so there's something unifying about the unit's position. And in fact, we're going to see that that unifying characteristic is very useful to us when we're trying to convert between values. Okay, so this commonality in the unit's position we can leverage in order to do base conversion, but we'll save that for the next presentation. Okay, and that's where we'll leave off, and I'll see you next time. Thanks.